Right now, somewhere above you tonight, there is a star that might already be gone. Betelgeuse, the burning red shoulder of Orion, is a dying giant so massive that if it replaced our sun, its surface would stretch out almost to Jupiter. For more than 100 years, it hid a secret companion star, one that only an astronomer managed to catch on camera. It has dimmed without warning, brightened without explanation, and startled astronomers awake more than once. Almost every secret has now been solved, except one, when it finally explodes. And it will not harm us. It will light our sky, day and night, for the better part of a year, closing out a death that may have already happened, centuries before you were even born. If tonight's story keeps you company the way Betelgeuse has kept ours for centuries, a like and a subscribe help this quiet corner of the sky reach a few more curious minds who need it. Settle in and get comfortable now. In 3, 2, 1, lift off. If you have ever stepped outside on a clear winter evening, away from the glow of porch lights and passing headlights, there is a good chance you have already met this star, whether or not you ever learned its name. Winter air tends to be unusually still and clear, scrubbed clean of the summer haze that can blur and dim a night sky, which is part of why this particular season offers some of the best stargazing conditions of the entire year. Look toward the eastern sky in autumn or straight overhead by the heart of winter, and you will eventually find 3 stars in a short, straight row, close enough together that the eye naturally links them into a single line. Ancient stargazers saw that row as a hunter's belt and built an entire figure around it. Broad shoulders, a raised arm, a sword hanging at his side, striding endlessly across the winter sky. Above, and to the left of that belt, marking one shoulder of the hunter, burns a star, unlike any other nearby, a deep, warm, orange-red point of light, the kind of color that stands out even to someone who has never studied a single constellation in their life. Finding it for yourself does not require any special equipment, only a clear sky and a little patience. Locate the 3 belt stars first, unmistakable once you know to look for them, close together and evenly spaced, unlike almost anything else nearby. Then look up and to the left toward the nearest bright, distinctly reddish star. That star has been watched, named, and wondered about by nearly every culture that ever looked up at a winter sky, and it is hanging in exactly the spot that farmers, sailors, and shepherds relied on for thousands of years to orient themselves, long before anyone thought to give it a name. Its name, as most people pronounce it today, is Betelgeuse. That name carries a small mystery all its own, the kind of story that tends to delight anyone who enjoys discovering how words survive their own history. It traces back to Arabic, to a phrase describing the hand of Al-Jawza, an old name for the great figure we now call Orion. Centuries ago, as medieval scholars worked to translate Arabic star catalogues into Latin and the languages of Europe, a single letter was misread, an easy mistake to make when copying unfamiliar script by candlelight. And that mistake was never corrected. The word that should have echoed something closer to hand instead came down to us sounding like the beginning of a name for a beetle, and it has been printed that way in star atlases ever since. It is a small human detail hiding inside one of the sky's oldest names, proof that even the most ancient, most familiar points of light in our sky carry the fingerprints of every person who has ever looked up, tried to make sense of what they saw, and pass that understanding on to whoever came next. The Greeks told their own version of this figure's story, casting him as Orion, a legendary hunter of enormous strength and even greater pride, a man who boasted he could kill every animal on earth. In most tellings, That boast is exactly what destroyed him. A scorpion, sent to humble him, delivered a fatal sting, and the gods placed both hunter and scorpion in the sky afterward, but on opposite sides of it, forever chasing one another around the heavens without ever quite meeting. That old story still plays out overhead every year, in a small, quiet way most casual stargazers never notice. Orion rules the winter sky, while Scorpius, his old rival, rules the summer sky, and the two are never visible at the same time from most of the United States, one always setting beneath the horizon just as the other rises to take his place. Orion holds another distinction that has nothing to do with mythology and everything to do with geography. It straddles the celestial equator, the imaginary line in the sky directly above Earth's own equator, which means it is one of the very few constellations visible, at least for part of the year, from virtually every inhabited place on the planet. A stargazer in Minnesota and a stargazer in rural Australia can, at certain times of year, look up and find the exact same hunter striding across their very different skies, Betelgeuse glowing the same shade of orange-red in each. Strip away the mythology and the medieval translation error, though, and what remains is one of the strangest, most extreme objects the night sky has to offer, hiding in plain sight inside one of its most familiar shapes. This is not merely a bright star. It is a red supergiant, a category reserved for only the most massive, most short-lived stars in the entire galaxy, and it is nearing the very end of its life. Nearly everything that makes Betelgeuse beautiful to the naked eye, its size, its color, its brightness, is also a sign of a star already deep into its final stages, burning through the last of what it has left. Astronomers have a particular fondness for the phrase hiding in plain sight when they talk about stars like this one, because it captures something true about how science actually works. The star was never hidden. It has been visible to anyone with functioning eyesight for as long as human beings have looked up at the night sky. What took centuries to uncover was never the star itself, but everything happening inside it. To understand just how enormous this star truly is, it helps to try a small experiment that astronomers themselves like to use. Imagine, for a moment, that Betelgeuse took the place of our own Sun at the center of the solar system. Mercury would disappear first, swallowed whole. Venus would vanish next, then Earth and everything on it, then Mars beyond it. The star's outer surface would keep expanding past the asteroid belt, past millions upon millions of miles of open space, and would finally come to rest somewhere near the orbit of Jupiter itself, the fifth planet from the Sun, and ordinarily one of the largest bodies in our entire solar system. A star whose surface can, at least in the imagination, reach out and brush against Jupiter's orbit is a star roughly 700 times wider than the Sun we actually have. Looked at a different way, more than 400 million suns, each one identical to our own, could theoretically be packed inside a sphere the size of Betelgeuse with room left over. Size alone does not tell the whole story, because Betelgeuse is not simply large, it is also strangely light for its size, in the way a great, hollowed-out log can look enormous while still being easy for one person to lift. Its outer layers are so thin and so loosely held together that its total mass comes out to somewhere between 16 and 19 times the mass of the Sun, a number astronomers have had to refine again and again as better instruments and sharper calculations have come along over the years. That threshold matters enormously for how a star's story eventually ends. Stars with roughly 8 times the mass of the Sun or more are destined eventually to die in a supernova. Smaller stars, including our own Sun, are gentler in their old age, shedding their outer layers slowly and settling into a small, dense ember called a white dwarf, fading quietly rather than exploding. At somewhere between 16 and 19 solar masses, Betelgeuse sits comfortably, or perhaps uncomfortably, on the violent side of that dividing line. And despite that comparatively modest mass for such a colossal body, Betelgeuse pours out light at a genuinely staggering rate, somewhere between 7,500 and 14,000 times as much light as the Sun produces every second. If the Sun is a porch light left on for a summer evening, Betelgeuse is a lighthouse beacon, visible from so far away that entire ships could steer by it without ever seeing the shore. And yet, for all that light, Betelgeuse is one of the coolest stars shining that brightly anywhere in the winter sky. And that is exactly why it wears such a deep orange-red color instead of a blue-white one. Just below and to the right of Orion's raised arm sits Rigel, another brilliant star marking the hunter's foot, burning hot and blue-white the way a welder's torch does. Betelgeuse, by contrast, simmers at a surface temperature of roughly 5,800 degrees Fahrenheit, noticeably cooler than our own Sun, whose surface runs closer to 10,000 degrees Fahrenheit. That lower temperature is exactly why Betelgeuse glows red rather than white or blue. The same basic principle at work when a blacksmith's iron shifts from a dull orange toward a blinding white as it grows hotter inside the forge. The star is, in a very real sense, wearing its own temperature on its sleeve, its color a direct, visible readout of a furnace running cooler than most. That contrast between the two stars is visible to the naked eye on any clear winter night. No equipment necessary, one of the very few places in astronomy where a genuinely advanced scientific idea, the direct relationship between a star's temperature and its color, is written plainly across the sky for anyone to read. Exactly how far away Betelgeuse sits has proven surprisingly difficult for astronomers to pin down, which is itself a small, humbling reminder of how much uncertainty still surrounds even one of the sky's most closely studied stars. The best current estimates place it somewhere between 500 and 650 light-years from Earth, a range that has narrowed only gradually, as different methods keep producing slightly different answers. Part of the difficulty is almost comic in its irony. Betelgeuse is so bright that it overwhelms some of the very instruments designed to measure stellar distances with precision, the same way a photograph taken too close to a bonfire washes out into an overexposed blur. Some of the most sophisticated distance-measuring spacecraft ever launched simply cannot get a clean reading on a star this brilliant. A light year, for anyone unfamiliar with the term, is simply the distance that light travels across the emptiness of space in a single year, moving at roughly 670 million miles an hour, the fastest speed anything in the universe is capable of reaching. That means the light striking your eye, on any night you happen to spot this star for yourself, left its surface centuries ago, long before Christopher Columbus's ships ever left the dock, back when the light, now reaching Earth, had already been crossing the emptiness between the stars for longer than the entire history of the United States. Here is where the story turns genuinely strange, in a way that has nothing to do with mythology or a medieval translator's slip of the pen. Our own sun has been shining for roughly 4.5 billion years and still has enough hydrogen fuel in its core to keep going for another 5 billion years or so. Betelgeuse, by comparison, is almost unbelievably young, current estimates put its age at fewer than 10 million years old, a sliver of the Sun's lifespan so small it barely registers, closer in cosmic terms to a newborn than to an elder. And yet this newborn star has already burned through every scrap of hydrogen fuel at its core and swollen into its current bloated, unstable form, already standing at a threshold most stars never reach until they are billions of years old. The explanation turns out to be almost intuitive once it is laid out plainly. The more massive a star is, the harder its own gravity presses inward on its core, and the harder the core has to labor just to hold itself up against the crush of its own weight. A modest star, like the Sun, burns its fuel patiently, a low, steady flame capable of lasting for billions of years. A star built on the scale of Betelgeuse burns recklessly by comparison, spending its fuel in a tiny fraction of that time, living out an entire lifetime in what amounts to, on a cosmic clock, little more than a single afternoon. Stranger still, there is real reason to believe that Betelgeuse has not always looked the way it looks tonight. Astronomical records, reaching back roughly 2,000 years, some from Mediterranean antiquity and some from Chinese court astronomers, keeping careful nightly logs of the sky, describe a star in this exact position with a noticeably different color, closer to yellow or pale orange than the deep red burning there now. If those ancient descriptions are accurate, and a number of researchers now believe they likely are, it would mean that within the span of recorded human history, a star has visibly changed color in Earth's sky, cooling and reddening as it has continued swelling outward. Modern astronomers take these ancient accounts seriously, cross-checking them against independent lines of evidence rather than dismissing them as poetic imprecision, precisely because they so rarely find good reason to doubt them. Stars are not supposed to change so dramatically within a mere 2,000 years, a blink of an eye by the standards of stellar evolution, and that mismatch alone tells you something important. Whatever is happening inside Betelgeuse right now appears to be happening unusually fast, even judged against the already accelerated standards of a star that was living on borrowed time to begin with. Few people alive today have spent more hours trying to understand exactly what is happening inside that star than Andrea Dupree, an astronomer with the Center for Astrophysics at Harvard and Smithsonian in Cambridge, Massachusetts. For years, Dupree and her colleagues have trained some of the most sophisticated instruments ever built, including the Hubble Space Telescope, on this single star, treating it less like a distant, indistinct point of light and more like a patient under long-term observation. It is, in some ways, an unusual career to have built, returning again and again across decades to the same star in the same familiar corner of the winter sky. But Betelgeuse has rewarded that patience. It happens to be one of the very few stars close enough and large enough for telescopes on Earth to make out actual surface detail, rather than the simple, undifferentiated point of light that nearly every other star in the galaxy presents. Astronomers have captured real images of its surface, showing bright and dark patches drifting slowly across it, something like sunspots on an almost unimaginably larger scale, evidence of enormous bubbles of hot gas rising and falling within the star's outer layers, some of them large enough on their own to swallow our entire solar system many times over. Watching this star closely, in other words, is not just possible. It may be one of the only real chances astronomers will ever get to watch a star this size, this close to the end of its life, up close and in something resembling real time. That rarity is precisely why Betelgeuse matters so much to modern astronomy, and why it turns up again and again in research papers, observatory schedules, and now, increasingly, in headlines far beyond the scientific press. Red supergiants are among the most consequential stars in the entire galaxy, not because there are many of them scattered across the sky, but because of what they eventually leave behind. Nearly every atom of calcium in your bones, every atom of iron carried through your blood, every atom of oxygen filling your lungs at this very moment was forged inside a star very much like this one during the final, violent chapter of its life, then scattered outward across the galaxy to eventually become part of new stars, new planets, and in at least one case, part of you. This is not a poetic exaggeration or a turn of phrase meant to sound profound. It is a literal, well-established fact of physics, confirmed and refined by decades of study. Those elements were not present in the early universe at all, until stars, like this one, manufactured them deep in their cores and scattered them outward in death. Understanding exactly how a star like Betelgeuse behaves as it approaches that final chapter is not simply an academic exercise carried out for its own sake. It is, in a very real sense, an attempt to understand where the raw material of life itself actually comes from. Someday, and this is not a matter of if, but only a matter of when, that process will reach its natural conclusion. A star of this size cannot simply fade away quietly the way smaller stars like the Sun eventually will. When Betelgeuse finally exhausts every fuel source available to it, its core will collapse in on itself in a fraction of a second, triggering one of the most violent, most luminous events the universe is capable of producing, a supernova. For a few brief weeks, a single exploding star like this, one can outshine every other star in its entire galaxy, combined, 100 billion suns worth of ordinary starlight, briefly matched by one dying giant. Exactly when that moment will arrive is a question that has occupied and divided serious astronomers for years, a question we will return to later in this video. For now, it is enough to understand that the star hanging quietly in Orion's shoulder tonight, the one so many people have glanced at without a second thought, is already living on borrowed time, counting down toward an ending that is certain in its arrival and almost entirely uncertain in its timing. To understand why a star reaches this particular stage at all, it helps to think of a star's life the way you might think of a long, slow-burning fire that has to keep changing what it burns as its original fuel runs low. For most of a star's life, it survives by fusing hydrogen, the simplest and most abundant element in the universe, into helium, deep within its core, releasing the light and heat that keep the star shining and holding it up against its own gravity. That stage can last for billions of years in a star like the Sun. But once the hydrogen at the core finally runs out, the star has no choice but to search for a new fuel source. And it does something that seems almost contradictory at first. Its core shrinks and grows hotter, while its outer layers swell outward into an enormous, puffed-up shell, cooler and redder than before. That is the transformation that turned Betelgeuse from an ordinary, hydrogen-burning star into the swollen red supergiant hanging in the winter sky tonight. That swelling into a red supergiant is only the first of several transformations still ahead of it. Deep inside its core, once the hydrogen is gone, a star begins fusing helium into carbon, and eventually, if it survives long enough, carbon into still heavier elements. Each new fuel burning faster and less efficiently than the one before it, like a fire forced to switch from good dry firewood to damp kindling as the night wears on. Exactly which of these stages Betelgeuse has already reached and how much fuel remains at each one turns out to be one of the more contested questions in modern astronomy, one we will return to later in this video. Red supergiants are not especially rare across the galaxy as a whole, but they are exceptionally rare close to home. Most of the ones astronomers know about sit thousands of light years away, distant enough that even the most powerful telescopes struggle to study them in any real detail. Betelgeuse, at only a few hundred light years out, is by a wide margin the nearest example of this kind of star, which is precisely why it receives the kind of sustained, almost obsessive scientific attention that few other stars in the sky can claim. That rarity gives Betelgeuse an outsized importance in the scientific literature, cited and recited in paper after paper as the benchmark case, the one example every new theory about a dying star's final centuries eventually has to be checked against. Hubble has not worked alone in this effort either. Radio telescopes, infrared observatories, and giant ground-based instruments scattered across multiple continents have all, at one point or another, turned their attention toward this single star, each one contributing a different piece of a picture no single telescope could ever capture alone. Capturing an actual image of a star's surface, rather than the single point of light every other star provides, requires a trick borrowed from precision engineering, combining the light collected by multiple telescopes, sometimes separated by great distances, so that together they function as one instrument far larger than anything that could ever be built as a single machine, not unlike a group of people cupping their hands around their ears to hear a distant sound more clearly than any one of them could alone. In a very real sense, Betelgeuse functions as humanity's one red supergiant close enough to actually watch. Orion itself offers no shortage of remarkable neighbors for Betelgeuse to share the sky with, which is part of why this particular stretch of winter sky has captivated stargazers for so long. Hanging below the three belt stars is a faint smudge of light, visible even to the unaided eye on a clear, dark night, a vast stellar nursery known as the Orion Nebula, roughly 1,300 light-years away, where thousands of new stars are being born out of collapsing clouds of gas and dust even now, at this very moment, while you listen to these words. Through even a modest backyard telescope, that faint smudge resolves into something genuinely breathtaking, glowing wisps of pink and green gas wrapped around a tight cluster of newborn stars, still bright enough to light up the cloud that bore them. Rigel, blazing blue-white at the hunter's opposite foot, and Bellatrix, marking the second shoulder, round out a constellation that manages to hold, within a single glance on a clear winter night, a stellar nursery actively giving birth to new suns, several stars comfortably settled into the prime of their lives, and Betelgeuse, a star already standing at the very edge of its own ending. Few patches of sky, anywhere, offer such a complete, visible summary of a star's entire life story gathered into one place. And in just the last few years, this particular star has offered an unusually direct answer to some of astronomy's oldest questions about how stars like it behave in their final act, not through any single dramatic breakthrough, but through a string of discoveries arriving one after another, each one reshaping what astronomers thought they understood about the star, quietly holding down Orion's shoulder. Some of what follows will feel less like the discovery of a new scientific fact and more like the slow unraveling of a very old, very patient secret, one that Betelgeuse appears to have been keeping for far longer than anyone ever suspected. Much of what astronomers know about Betelgeuse's long-term behavior does not come from professional observatories alone. For nearly 2 centuries, amateur stargazers, ordinary people with a telescope, a notebook, and genuine curiosity have tracked this star's changing brightness night after night, season after season, and submitted their careful observations to organizations built specifically to collect them, chief among them a nationwide network of volunteer observers who have quietly logged Betelgeuse's brightness for generations. That patient, unglamorous record-keeping, carried out largely by hobbyists rather than professional scientists, has produced one of the longest continuous brightness histories of any star in the sky, stretching back further than most professional survey instruments have even existed. It is, in its own quiet way, one of the largest ongoing citizen science projects in the history of astronomy, and it would prove essential to understanding what happened to this star next. When the moment came that Betelgeuse needed watching more closely than ever before, it would not only be professional astronomers with access to space telescopes who answered the call. At least one of those dedicated amateur observers would go on to be named directly as a co-author on the serious scientific paper that eventually explained what everyone was seeing, a rare and fitting tribute to 2 centuries of patient, unpaid dedication. For most of the 20th century, in fact, Betelgeuse behaved about as predictably as an already unpredictable dying star can behave. It brightened and dimmed on a fairly regular rhythm, waxing and waning across a cycle lasting a little longer than a year. The ordinary breathing pattern of a star, swelling and contracting as it burns through what remains of its fuel. Underneath that yearly rhythm, astronomers had also noticed a second, much slower pattern layered on top of the first, one that took nearly 6 years to complete a full cycle, and that nobody could fully explain, a puzzle quietly set aside for another day. Astronomers who studied the star decade after decade came to know its dominant rhythm, the way a longtime neighbor comes to know the particular creak of somebody else's screen door, without ever having to think about it twice. It was familiar. It was, by the standards of a dying star, almost restful to watch. Then, in the closing months of 2019, that familiar rhythm broke. Betelgeuse began to dim, not in the small, expected way it always had before, but dramatically, rapidly, and with no clear explanation in sight. Astronomers who had spent their entire careers watching this particular star had never once seen anything like it. Within a matter of weeks, one of the 10 brightest stars in the entire night sky was fading from view, and for a little while, nobody watching it had any idea why. At first, it looked like nothing more than an unusually deep dip in a rhythm astronomers already knew well. Betelgeuse's brightness had always risen and fallen on that familiar year-long cycle, and every so often, that cycle reached a slightly deeper minimum than usual. Backyard observers tracking the star through their own telescopes noticed it first in the simplest way possible. A star that had always been easy to spot, even from a porch or a driveway in a modestly lit neighborhood, was becoming steadily harder to find. But as October turned to November, and November to December, the dimming kept going, well past the point where the star should have started brightening again. The decline did not happen all at once. Through October of 2019, the dimming was noticeable, but not yet alarming, the kind of dip careful observers might attribute to ordinary variation. By November, it had deepened further, drawing the first real attention from professional astronomers monitoring the star's brightness through international observation networks. December brought a steeper decline still, and by the final week of the year, Betelgeuse had already grown noticeably fainter than anything in the modern observational record. January proved to be the most dramatic month of all, with the star's brightness continuing to plunge day after day, prompting the flurry of observation campaigns, telescope proposals, and public speculation that would come to define the entire episode. It was not until the star finally leveled off in early February, hovering near its faintest point for roughly 2.5 weeks, that anyone could say with confidence the freefall itself had ended, even though the explanation for it remained, at that point, still very much unresolved. By the time the dimming reached its deepest point, Betelgeuse had lost roughly 2/3 of its usual brightness, a decline unlike anything recorded in more than a century of careful observation. The star tumbled out of its usual place among the 10 brightest points of light in the entire night sky, slipping all the way down to roughly 21st on that list, a demotion so unusual that it made headlines far beyond the world of professional astronomy. For a star that generations of stargazers had come to rely on as one of the surest, steadiest lights in the winter sky, that kind of fall was almost impossible to ignore. News of the dimming spread quickly, and not always calmly. Headlines speculating that Betelgeuse might be on the verge of exploding into a supernova began appearing in newspapers and on television broadcasts around the world, feeding a wave of public fascination that occasionally tipped over into genuine alarm. Late-night television hosts made jokes about it. Newspaper science sections ran explainer pieces attempting to walk readers through what a nearby supernova might actually mean for life on Earth, usually concluding, correctly, that there was nothing to fear regardless of when the star eventually did explode. Online discussion boards dedicated to astronomy filled with amateur speculation, some of it well-informed, much of it not. For a few remarkable weeks, the fate of a single, extremely distant star became genuine dinner-table conversation in households that had never previously given astronomy a second thought. Proof that a sufficiently strange occurrence in the night sky can still capture the public imagination the way it always has, going back to every eclipse, comet, and unexplained light that human beings have ever paused to look up and wonder about. Some of that excitement was understandable. A star this size, this close, going supernova within a human lifetime would be one of the great astronomical events in recorded history, and the dimming was, at the very least, consistent with the kind of instability a dying star might show in its final years. But professional astronomers, including Dupree and her colleagues, urged caution from the very beginning. A star does not necessarily dim because it is about to explode. Plenty of far more ordinary explanations existed, and ruling them out, one by one, was the only responsible way to find out what was actually happening. Reporters unfamiliar with the normal pace of peer-reviewed research sometimes struggled to understand why astronomers were not simply announcing an answer within days, a frustration that, in its own small way, revealed just how differently science and the news cycle are built to operate. For Dupree, who had already spent years studying this star before the dimming ever began, the episode marked an unexpected turning point in a career built around patient, incremental observation. Suddenly, a star she had watched quietly for so long was making front-page news, and the pressure to produce a careful, defensible answer rather than a rushed one weighed heavily against the enormous public appetite for an immediate explanation. That tension between the slow pace good science actually requires and the fast pace the public understandably wanted would come to define much of how the following 2 years of research unfolded. Telescopes around the world and in orbit above it turned their attention toward Orion's shoulder in a way that had rarely happened for any single star before. Dupree's team secured time on the Hubble Space Telescope, using its ultraviolet instruments to look for changes in the star's outer atmosphere that would be invisible to any telescope confined to the ground. On the other side of the world, at the Very Large Telescope, a facility perched high in the dry mountains of northern Chile, another team pointed a specialized instrument called Sphere directly at the star, hoping to capture something no one had ever managed to capture cleanly before, an actual picture of Betelgeuse's surface, rather than the single blurred point of light every other star in the sky provides. Radio telescopes contributed their own piece of the puzzle as well. At the Very Large Array in New Mexico, a sprawling collection of enormous dish antennas, familiar to many from documentaries and films about the search for signals from deep space, astronomers measured the temperature of gas high in Betelgeuse's outer atmosphere during the months surrounding the dimming. What they found matched the emerging picture perfectly, temperatures running noticeably colder than usual, further confirmation that something genuinely unusual had disturbed the star's outer layers, not merely its visible surface. What the instrument in Chile captured became one of the defining images to come out of the entire episode. Researchers compared a photograph of Betelgeuse's disk taken in January of 2019, before any dimming had begun, against a second photograph of the same star taken in December of that same year, near the height of the crisis. In the earlier image, the star appeared as a roughly even, softly glowing sphere. In the later one, an entire portion of that sphere, roughly the lower half, as seen from Earth, had visibly darkened, as though a shadow had been drawn across part of the star's face. Viewed side by side, the effect was almost unsettling to look at. A familiar, softly rounded star suddenly appearing lopsided, as though something had taken a bite out of its lower half. Astronomers who had spent careers looking at this exact point of light had genuinely never seen anything resembling it before. The reason only part of the star appeared to darken, rather than the whole visible disk at once, came down to simple geometry. The eruption had occurred on one side of the star, and the resulting dust cloud drifted outward mostly in that same direction, meaning it blocked light only from the portion of Betelgeuse's surface that happened to lie behind it. As seen from Earth's particular vantage point, a stargazer positioned somewhere else in the galaxy, looking at Betelgeuse from a different angle entirely, might not have seen it dim at all. It was the first time in the history of astronomy that anyone had photographed a star changing shape and brightness this dramatically in real time, a visual record that made an already strange story impossible to dismiss as mere statistical noise in a light curve. While the images from Chile showed astronomers what was happening, it fell largely to Dupree's team, working with ultraviolet data from Hubble, to explain why. Piecing together observations gathered before, during, and after the dimming, they traced the origin of the disturbance back to earlier than anyone had initially suspected, to a violent event in the star's outer layers, occurring sometime between January and March of 2019, nearly a full year before the dimming became visible to the naked eye on Earth. The team announced their result in July of 2025, a probable direct detection of Betelgeuse's long-predicted companion. The word probable was chosen carefully and deliberately. The detected signal was real and promising, closely matching the position and estimated mass the 2023 model had predicted, somewhere in the neighborhood of 1.5 times the mass of our Sun. But the signal alone was not yet strong enough, by the rigorous standards astronomers hold themselves to call the discovery fully confirmed. It was a milestone, the first real evidence in over a century of speculation. But the astronomical community, mindful of how many false alarms and premature announcements had come and gone in fields like this one, wanted more. Howell's team was not the only one watching that winter. Observatories on multiple continents had adjusted their own schedules to attempt observations of the same critical window, recognizing that a confirmed detection, however it came, would settle a question that had outlasted the careers of astronomers who first went looking for an answer generations earlier. That kind of coordinated, overlapping effort, multiple independent teams converging on the same brief opportunity using different instruments and different techniques, has become increasingly common in modern astronomy, offering a built-in safeguard against any single team's result being mistaken, misread, or simply unlucky. That confirmation arrived within months. A separate team, led by researcher Anna O'Grady at Carnegie Mellon University, had also been watching the same critical window, using a different pair of instruments entirely: the Chandra X-ray Observatory, a space telescope built to detect the kind of high-energy light given off by extremely hot or violent objects, and the Hubble Space Telescope, already familiar from its central role in explaining the Great Dimming. The difference between July's cautious, probable detection and October's confirmed one came down to the kind of evidence each team had gathered. Howell's team had captured a single, clear image, powerful evidence on its own, but a single image, however convincing, still carries some inherent uncertainty. O'Grady's team, working with instruments sensitive to entirely different wavelengths of light, provided independent corroboration using physics unrelated to simple visual imaging. When two fundamentally different methods arrive at the same conclusion, the case for that conclusion becomes dramatically stronger than either method could establish alone. The key evidence came from what the observations did not find as much as what they did. A white dwarf, or neutron star, orbiting this close to a star as vast as Betelgeuse, would typically be expected to produce a detectable stream of X-ray emission, generated as material from the giant star's outer atmosphere gets pulled toward the smaller, far denser object and heats up dramatically in the process. O'Grady's team searched carefully for exactly that kind of signature and found essentially none of it. The absence of that telltale X-ray glow was, in its own way, just as informative as a positive detection would have been. Combined with the ultraviolet data, which showed a temperature and brightness profile consistent with an ordinary, if young, star rather than anything exotic, the picture that emerged left little room for alternative interpretations. Before the surface mass ejection explanation took hold, astronomers seriously entertained several competing ideas, each one carefully tested, and, one by one, set aside. Some wondered whether an enormous, unusually cool patch on the star's surface, essentially a sunspot on a scale almost impossible to picture, might be responsible, temporarily, reducing the light coming from one region of the star. Others considered whether the dimming might be an early signal of some deeper, more fundamental change inside the star itself, a genuine step toward its eventual collapse rather than a surface-level event. Infrared observations proved decisive in ruling out that second, more alarming possibility. Dust blocks visible light far more effectively than it blocks infrared light, re-radiating much of the energy it absorbs at those longer wavelengths instead of simply erasing it. When astronomers checked Betelgeuse's infrared brightness throughout the entire episode, they found it had barely changed at all, even while its visible brightness was collapsing by the day. The star's true energy output, in other words, had never actually dropped. Something was simply standing between that light and Earth, and that distinction, subtle as it sounds, made all the difference in understanding what was and was not happening inside a star nearing the end of its life. Each rejected hypothesis still contributed something useful along the way, narrowing the range of remaining possibilities and sharpening the questions the data still needed to answer. The ordinary, unglamorous rhythm of how scientific consensus actually gets built. The event itself, once reconstructed, turned out to be something astronomers had never directly witnessed happening to any star besides our own sun. Deep within Betelgeuse's turbulent outer layers, one of those enormous convective bubbles of hot gas, the same kind of roiling, rising cell described earlier, grew powerful enough to punch through the star's visible surface entirely. In doing so, it hurled an enormous quantity of stellar material out into space in a single violent event astronomers now call a surface mass ejection. The scale of what erupted is difficult to overstate. The plume of ejected material measured roughly 1 million miles across as it left the star, a single outburst wider than 4 times the distance separating the Earth from the Moon. Every red supergiant loses some mass continuously throughout its life, streaming material outward in what astronomers call a stellar wind, a slow, steady breeze of gas drifting off the star's outer layers even under perfectly ordinary conditions. What made the 2019 event so remarkable was not that Betelgeuse lost mass, since it does that constantly, but how much it lost in one single, concentrated burst. Astronomers calculated that the eruption alone released an amount of material comparable to what the star would ordinarily shed through its steady stellar wind across an entire year, all compressed into a single, sudden event rather than spread evenly across 12 months. It was the difference between a slow, steady leak and a single, sudden rupture, both moving comparable amounts of material in the end, but in dramatically different fashion. There was a second factor at work as well, one that had nothing to do with the dust cloud at all. Quite apart from the surface mass ejection, Betelgeuse happened to be moving through the natural low point of its ordinary year-long pulsation cycle at almost exactly the same time, the same regular dimming the star always experiences as it rhythmically swells and contracts. On its own, that seasonal dip would have been unremarkable, barely noticed by anyone outside the community of dedicated variable star observers. But arriving at the same moment as the dust cloud, it stacked directly on top of the obscuration already underway, compounding it. Astronomers sometimes compare this kind of overlap to 2 unrelated problems, striking a radio signal at once, a weak transmitter and a passing storm, each one a minor annoyance alone, but together producing static bad enough to lose the station entirely. It was the coincidence of these 2 ordinarily unremarkable events, a routine dimming cycle and an unprecedented eruption, both crossing paths at the same unfortunate moment, that produced a dip in brightness deep enough to spark headlines around the world. Untangling how much of the dimming belonged to the dust cloud and how much belonged to the ordinary pulsation cycle required exactly the kind of long, unbroken brightness record that only patient, dedicated observation could provide, which is precisely where the long tradition of amateur stargazing mentioned earlier proved essential. Thomas Calderwood, an amateur astronomer affiliated with a nationwide association of volunteer variable star observers, had spent years contributing his own careful brightness measurements of Betelgeuse to the same kind of shared record built up by generations of hobbyists before him. When Dupree and her colleagues finally published their explanation of the Great Dimming in a peer-reviewed astronomical journal, Calderwood's name appeared alongside theirs as a full co-author. His years of patient backyard observation folded directly into one of the most significant stellar discoveries of the decade. It remains a small, quietly remarkable detail in a much larger story. One of the key figures who helped explain the strangest thing this star had done in a century was not stationed at a professional observatory at all, but was simply someone who had never stopped looking up. The explanation did not arrive quickly. Confirming the surface mass ejection theory, ruling out the alternatives, and combining evidence from multiple telescopes into a single coherent picture took Dupree and her colleagues roughly 2 years of careful work following the dimming itself. Their full explanation was not published until 2022, long after public attention had already moved on to other things. That gap says something important about how real science actually operates, in sharp contrast to the pace of a news cycle. The public panic over a possible supernova had come and gone within a matter of weeks. The actual scientific answer took years of patient work, careful data collection, and rigorous cross-checking before anyone was willing to call it settled. Taken together, the imagery from Chile and the ultraviolet evidence from Hubble amounted to something astronomers had wanted to witness directly for a very long time: definitive proof that a star other than the Sun could shed a piece of itself in a single, sudden, observable event, and that the resulting material could be tracked in real time, from eruption to visible dust cloud to gradual dispersal. Astronomers studying distant red supergiants, stars too far away to ever photograph in this kind of detail, could now use Betelgeuse's documented eruption as a real-world reference point, a known example against which to compare and interpret whatever they could indirectly detect happening on other, more distant giants nearing their own endings. In that sense, the Great Dimming's value extended far beyond this single star. Papers modeling dust formation around aging stars, papers studying the late-stage winds of massive supergiants, papers attempting to predict how similar stars elsewhere in the galaxy might behave, all of them, in the years that followed, found reason to cite Betelgeuse's own well-documented episode as their clearest available example. It became a kind of calibration event for an entire field of study. By April of 2020, roughly 3 months after the deepest point of the dimming, Betelgeuse had already climbed back to a brightness level it had not managed to reach in over a year, a milestone that made its own share of headlines, this time celebratory rather than alarmed. By early summer, the star had essentially returned to a range indistinguishable from its behavior in the years before the eruption, at least as far as raw brightness was concerned. Stargazers who had grown accustomed to searching a little harder to find Orion's dimmed shoulder each night gradually noticed the opposite happening instead, the star creeping back toward its usual prominence week after week, until it once again anchored its familiar spot in the winter sky without any special effort required to locate it. The dramatic, headline-grabbing portion of the story was over in less than a year from start to finish. Even so, a small, permanent asterisk had been added to Betelgeuse's long observational history, a single, unmistakable entry in more than a century of otherwise unremarkable brightness records. What lingered, quietly, in the data astronomers kept collecting would take considerably longer to fully understand. The familiar year-long pulsation rhythm, the steady rise and fall that had defined Betelgeuse's behavior for as long as anyone had been carefully recording it, did not resume on schedule. Instead, that rhythm went quiet for more than 2 years, an unprecedented silence in a beat that had been reliable for generations. Dupree herself has been characteristically direct about how much of this remains unresolved. Whatever violent reorganization took place inside the star during the eruption appears to have disrupted the delicate internal balance responsible for that steady pulse, though exactly how or why the disruption lasted as long as it did is a question current models cannot yet fully answer. It is a little like a bell struck once, far too hard, that keeps ringing afterward, but never again with quite the tone it had before the blow landed. The star's outer atmosphere itself seemed to bear the marks of the disturbance as well. In the aftermath, the visible surface measured slightly cooler than it had before the eruption, and the thin, superheated layer just above it, the chromosphere, thinned out into something noticeably less dense. Both changes were modest on their own, but together they painted a picture of a star still visibly unsettled, long after the dust cloud that made headlines had drifted away and stopped mattering to anyone watching from Earth. Some researchers see that lingering silence as a small but meaningful clue about how stars destabilize on their way toward eventual collapse, evidence that the internal machinery keeping a star like this one balanced against its own gravity can be knocked briefly out of rhythm by a large enough disturbance, even one that, in the broader scheme of the star's total mass, amounted to only a modest fraction of what it typically sheds in an ordinary year. If a single eruption could disrupt that rhythm for more than 2 years, it raises a natural question about what might happen as Betelgeuse draws closer to its true ending, when disturbances of this kind, or perhaps far larger ones, may become more frequent rather than less. This was not, in fact, the first time Betelgeuse had shed material into space, only the first time astronomers caught the process happening in such vivid, immediate detail. Careful study of the space surrounding the star has revealed multiple overlapping shells of previously ejected material, layered like the rings of a tree, each one marking an earlier episode of mass loss stretching back further than modern instruments can precisely date. The 2019 eruption simply became the first one anyone was fortunate enough to watch happen in real time, rather than discovering only after the fact, written into the star's surroundings like a fossil record. For astronomers studying how massive stars spend their final years, the entire episode amounted to an unplanned, once-in-a-generation experiment, one that nature ran on its own schedule and simply allowed humanity to observe up close. Watching that process happen in a single, documented event, rather than inferring it indirectly from stars too distant to study in detail, gave researchers a level of insight that theory alone could never have provided. The Great Dimming also permanently changed how closely the astronomical community would watch this particular star from that point forward. Observation campaigns that had once checked in on Betelgeuse occasionally now began monitoring it continuously, treating it less like a well-known but otherwise unremarkable neighbor and more like a patient whose condition genuinely warranted round-the-clock attention. Telescope time that might once have gone toward more distant, more exotic targets increasingly found its way toward this one familiar star instead, on the reasonable theory that a star capable of producing an event this dramatic, this unexpectedly, might well have more surprises left to offer. Every observatory capable of studying red supergiants in fine detail now had an obvious reason to keep at least one instrument trained on Betelgeuse at all times, aware that whatever happened next to the nearest example of this kind of star anywhere in the sky was unlikely to happen quietly. It was a shift in attention that would pay off almost immediately in ways nobody quite anticipated. For a scientific community that had just spent 2 years painstakingly reconstructing one of the most dramatic events ever observed on a star besides the Sun, one older puzzle remained a quiet, persistent reminder of how much about Betelgeuse still went unexplained. Long before 2019, astronomers already knew Betelgeuse carried a second, slower rhythm layered beneath its familiar year-long pulsation, a puzzling cycle lasting nearly 6 years that nobody had ever been able to account for. The surface mass ejection explained the dimming. It explained the star's strange, lingering silence afterward. It explained nothing at all about that older, 6-year puzzle, which had been sitting quietly in the data for more than a century, waiting for an explanation that would turn out to be even stranger than anything the dimming itself had revealed. Part 3. That 6-year rhythm had been sitting in the observational record for longer than anyone actively studying it had been alive. The earliest formal records of this longer pattern trace back to observers working in the very first years of the 1900s, long before anyone had the tools to seriously investigate what might be causing it. Layered beneath the star's familiar, roughly year-long pulsation, a second, much slower wave rose and fell across a cycle lasting nearly 6 years before repeating. Each subsequent generation of astronomers inherited the same puzzle from the one before it, confirming the pattern kept recurring with each passing decade, without ever managing to explain why. Unlike the shorter rhythm, which matched the ordinary swelling and contracting every red supergiant experiences as it ages, this longer cycle never fit neatly into any of the standard explanations for why a star's brightness changes. It became, in its own understated way, one of the most durable open questions in the study of this particular star, outlasting entire scientific careers spent trying to answer it. Over the decades, astronomers proposed several possible explanations, each one eventually falling short in one way or another. Some suggested the cycle might come from an unusually large convective cell, one of those enormous rising and falling bubbles of hot gas already known to churn beneath the star's surface, only far larger and slower than the ordinary ones. Others wondered whether it reflected some deeper, longer magnetic cycle, similar in spirit to the roughly 11-year cycle our own Sun goes through, but scaled up for a star of this size. Betelgeuse is far from the only red giant or supergiant known to display this kind of long, slow secondary brightness cycle either. Astronomers have catalogued similar long secondary periods in hundreds of aging giant stars scattered across the galaxy, a pattern common enough to have earned its own name in the scientific literature well before anyone settled on a single explanation for what caused it. For decades, the underlying cause of these long secondary periods remained one of the more persistent unsolved puzzles in the study of aging stars generally, not just for Betelgeuse specifically. A nagging possibility kept resurfacing every few years for this particular star, difficult to dismiss, and, for a long time, impossible to confirm that Betelgeuse was not alone out there at all, that some kind of companion object, orbiting close enough to interact with the star's outer layers, might be responsible. Astronomers had, in fact, gone looking for a companion before, at various points across the 20th century, using whatever instruments happened to be available at the time. Each earlier attempt came up empty, not necessarily because no companion existed, but because the instruments of those earlier decades simply were not sensitive enough or precise enough to separate a faint companion from the overwhelming glare of a star this bright. Those repeated failures very nearly convinced some researchers that the companion hypothesis was a dead end entirely, an appealing idea that observation after observation seemed determined to disprove. Confirming that theory directly required overcoming a genuine technical challenge. If a companion existed, it would need to orbit remarkably close to Betelgeuse to complete a full circuit in only 6 years, likely closer than Jupiter orbits our own Sun. At that distance, any companion would be sitting almost directly against the glare of a star, roughly 7,500 to 14,000 times as luminous as our own Sun, a star so bright it can overwhelm even the instruments built specifically to measure it precisely. Searching for a faint companion under those conditions is a little like trying to spot a single firefly hovering at the edge of a stadium's bank of floodlights during a night game, its small, real light almost entirely swallowed by everything blazing around it. The breakthrough that finally moved the companion theory from plausible guess to genuine prediction came in 2023, when a team at the Center for Astrophysics, the same institution where Dupree has spent her career, took a fresh approach to the problem. Led by researcher Morgan McLeod, the team gathered together every reliable brightness measurement of Betelgeuse they could find, stretching back roughly 127 years, and modeled how a companion star, if one existed, would need to move in order to produce exactly the 6-year pattern astronomers had been recording for generations. The model did more than simply support the old hypothesis. It made a specific, testable prediction, a companion star of a particular estimated mass, following a particular orbital path that should reach its farthest point from Betelgeuse, as seen from Earth, at a specific, calculable moment. For the first time, astronomers were no longer just guessing that a companion might exist. They knew, in principle, exactly where and when to look for it. What changed? Ultimately, to make a direct search, finally practical, was not any single breakthrough, but the steady accumulation of decades of technological refinement, finally reaching a threshold capable of meeting the challenge. Telescope mirrors grew larger and more precisely manufactured. Computer processing power, essential for techniques that require combining and analyzing thousands of individual exposures, increased by orders of magnitude. Space-based observatories, unavailable to any of the earlier generations of astronomers who had gone looking for this companion, offered entirely new wavelengths of light to search across, wavelengths where a faint companion might stand out more clearly against its overwhelming neighbor than it ever could in ordinary visible light alone. An astronomer working in the middle of the 20th century, however skilled, simply had no combination of tools capable of pulling off what the 2024 and 2025 observations eventually managed. The companion was not hiding especially well. In other words, humanity's instruments had only recently become good enough to find it. That prediction from the 2023 model came with an unforgiving catch. A companion orbiting this close to Betelgeuse would only be observable, even with the best instruments available, during a narrow window when its orbit carried it to maximum separation from the much larger star. Outside that window, it would either be lost entirely in the glare or hidden directly behind Betelgeuse from Earth's vantage point for roughly 2 years at a stretch. The entire opportunity resembled trying to photograph a single performer crossing a vast, brightly lit stage during the one brief moment a spotlight happened to swing across them, knowing that if the shot was missed, the next comparable chance would not come again for years. According to the model, that critical window was approaching fast, the closing days of 2024. The stakes surrounding that narrow window were genuinely high within the small community of astronomers who had spent years anticipating it. Missing the observation, whether due to bad weather at a critical observatory, an equipment malfunction, or simply losing out on telescope time to another research priority, would have meant waiting until Siwaha's next predicted return to maximum separation years later before getting another comparable opportunity. Multiple research teams began preparing months in advance, securing telescope time and refining their instruments in anticipation of that single, narrow opportunity, treating the closing weeks of 2024 with the kind of focused urgency usually reserved for far rarer astronomical events. On or around the 6th of December 2024, the predicted companion reached its point of maximum separation from Betelgeuse. A team led by Steve Howell, an astronomer with NASA's Ames Research Center, used a specialized instrument called Alapeke, mounted on the Gemini North Telescope high atop Mauna Kea in Hawaii, to attempt the observation. Mauna Kea rises nearly 14,000 feet above the Pacific, its summit sitting above a substantial share of the atmosphere responsible for blurring starlight in the first place. One of the reasons so many of the world's most powerful telescopes have been built there, rather than at lower, more convenient locations. Ordinarily, Earth's atmosphere blurs incoming starlight just enough to make precise, close-up imaging of this kind essentially impossible from the ground. One of the main reasons space telescopes exist in the first place. Alapeke offers a clever workaround, a technique astronomers call speckle imaging. By capturing many thousands of extremely short exposures, each one brief enough to freeze the atmosphere's blurring in place for that single instant, and then carefully combining them using specialized computer processing, astronomers can reconstruct an image far sharper than any single long exposure could ever achieve from the ground. When Howell's team finally analyzed their data months later, they found something, a faint point of light, sitting almost exactly where the model had predicted a companion should be. The team announced their result in July of 2025, a probable direct detection of Betelgeuse's long-predicted companion. The word probable was chosen carefully and deliberately. The detected signal was real and promising, closely matching the position and estimated mass the 2023 model had predicted, somewhere in the neighborhood of 1.5 times the mass of our Sun. But the signal alone was not yet strong enough. By the rigorous standards astronomers hold themselves to call the discovery fully confirmed. It was a milestone, the first real evidence in over a century of speculation, but the astronomical community, mindful of how many false alarms and premature announcements had come and gone in fields like this one, wanted more. Howell's team was not the only one watching that winter. Observatories on multiple continents had adjusted their own schedules to attempt observations of the same critical window, recognizing that a confirmed detection, however it came, would settle a question that had outlasted the careers of astronomers who first went looking for an answer generations earlier. That kind of coordinated, overlapping effort, multiple independent teams converging on the same brief opportunity, using different instruments and different techniques, has become increasingly common in modern astronomy, offering a built-in safeguard against any single team's result being mistaken, misread, or simply unlucky. That confirmation arrived within months. A separate team, led by researcher Anna O'Grady at Carnegie Mellon University, had also been watching the same critical window using a different pair of instruments entirely, the Chandra X-ray Observatory. a space telescope built to detect the kind of high-energy light given off by extremely hot or violent objects, and the Hubble Space Telescope, already familiar from its central role in explaining the Great Dimming. The difference between July's cautious probable detection and October's confirmed one came down to the kind of evidence each team had gathered. Howell's team had captured a single, clear image, powerful evidence on its own, but a single image, however convincing, still carries some inherent uncertainty. O'Grady's team, working with instruments sensitive to entirely different wavelengths of light, provided independent corroboration using physics unrelated to simple visual imaging. When two fundamentally different methods arrive at the same conclusion, the case for that conclusion becomes dramatically stronger than either method could establish alone. The key evidence came from what the observations did not find as much as what they did. A white dwarf, or neutron star, orbiting this close to a star as vast as Betelgeuse would typically be expected to produce a detectable stream of X-ray emission generated as material from the giant star's outer atmosphere gets pulled toward the smaller, far denser object and heats up dramatically in the process. O'Grady's team searched carefully for exactly that kind of signature and found essentially none of it. The absence of that telltale X-ray glow was, in its own way, just as informative as a positive detection would have been. Combined with the ultraviolet data, which showed a temperature and brightness profile consistent with an ordinary, if young, star rather than anything exotic, the picture that emerged left little room for alternative interpretations. Given how close the companion orbits, and given how old a system built around a dying supergiant like Betelgeuse ought to be, many astronomers had expected the companion, if found, to turn out to be a small, dense stellar corpse, either a white dwarf or a neutron star, the collapsed remains of an even earlier companion star that had already lived out its entire life and died first. The X-ray and ultraviolet data told a different story. Everything about the companion pointed toward an ordinary, young star, ordinary in the sense that it had not yet reached the midpoint of its own life, and roughly comparable in size to our own Sun, with an estimated mass somewhere between 1 and 1 6/10 times the Sun's mass. In other words, Betelgeuse, one of the oldest, most evolved stars in its immediate stellar neighborhood, had spent the better part of its life orbiting closely alongside a genuine youngster, the astronomical equivalent of discovering that a grandparent and a toddler had been born on the very same day and had lived next door to each other ever since. That mismatch matters enormously to astronomers who study how binary star systems, two stars gravitationally bound together, form and evolve in the first place. Stars that form together out of the same collapsing cloud of gas at roughly the same time are expected to age together as well, reaching each life stage in a comparable amount of time relative to their size. A star 16 to 19 times the mass of the Sun races through its entire life in a matter of a few million years, as established earlier, while a star closer to the Sun's own mass takes billions of years to reach the same relative milestones. Finding two such mismatched stars locked in a close, shared orbit means either they did not form at the same time after all, or something about the process of their formation stretched or compressed one star's development relative to the other in ways not yet well understood. Finding a star as advanced in its life as Betelgeuse, paired this closely with a companion still comparatively early in its own life, presents a genuine puzzle for existing models of how such systems come together. Researchers have proposed a few possible explanations for how such a mismatched pair might have arisen in the first place, though none has yet emerged as a clear consensus. One possibility involves Siwaha being a relative newcomer captured into orbit around Betelgeuse sometime after the larger star had already aged significantly, rather than the two having formed together from the start. Another possibility involves complex, still poorly understood dynamics in the crowded stellar nursery where Betelgeuse itself was born, capable, in principle, of pairing stars of very different ages under the right circumstances. Astronomers who study binary star formation more broadly have documented similar dynamical processes in other systems, though whether any of them specifically apply here remains untested. Whichever explanation eventually proves correct, if either does, the puzzle illustrates something important about how much remains genuinely unknown, even about processes as fundamental as how ordinary stars pair up in the first place, a reminder that binary star formation, despite being extremely common throughout the galaxy, is still far from completely understood in its finer details. For now, the honest answer is that astronomers have a confirmed, well-documented example of an extreme mismatch without yet having a fully settled explanation for how it arose. It stands as one of the most extreme mass mismatches ever confirmed in a binary star system anywhere in the galaxy. By September of that same year, the newly confirmed companion had earned an official name of its own, recognized by the international body responsible for approving star names. Officially naming a celestial object is rarely a fast or casual process. That organization, an international committee established specifically to standardize how stars and other astronomical bodies are named across every country and language, typically favors names drawn from historical, mythological, or cultural traditions connected to the object's constellation or region of sky, rather than allowing arbitrary or commercial names. Given Betelgeuse's own deep roots in Arabic astronomical tradition, choosing another word from that same linguistic heritage for its newly confirmed companion was a deliberate, careful decision, not an accident of convenience. Astronomers settled on Siwaha, an Arabic word meaning her bracelet, a fitting companion in more ways than one to Betelgeuse's own name, which traces back, as established earlier, to an old Arabic phrase describing the hand of the great figure we call Orion, a hand, and now, circling it closely, a bracelet. Few newly confirmed astronomical objects arrive with a name this carefully considered or this quietly connected to the star they orbit. News of the confirmed companion moved through the professional astronomical community quickly, generating the kind of genuine excitement that a century-old, well-known puzzle rarely produces upon finally being solved. Follow-up observation proposals were drafted within weeks, aimed at refining Siwaha's mass, its precise orbital shape, and its long-term prospects. The next opportunity to observe Siwaha near maximum separation and refine everything learned so far is expected sometime around November of 2027, when astronomers will get their next real chance to check their new model against the sky itself. The most direct confirmation yet of exactly how Siwaha influences Betelgeuse came only months later, in January of 2026, once again led by Dupree. It is worth pausing on the fact that the same astronomer sits at the center of both of Betelgeuse's most significant modern discoveries: the explanation for the Great Dimming, and now the direct evidence connecting Siwaha to the 6-year cycle. Careers in astronomy are rarely built around a single star this way. Dupree's sustained attention to this one object stretched across years and multiple entirely different lines of investigation, stands as its own quiet testament to how much can still be learned by simply refusing to look away from a familiar subject, even after most of the easy questions about it seem to have already been answered. Piecing together this latest confirmation required an unusual kind of patience, even by the standards of a field that already prizes patience above almost everything else. Rather than relying on a single dramatic observation, Dupree's team combed back through nearly 8 years of accumulated Hubble images and ground-based measurements, comparing subtle shifts in the density and motion of gas around Betelgeuse across that entire span, searching for a pattern consistent with Siwaha's known orbital path. What they identified was remarkable. A visible trail of unusually dense gas carved directly through Betelgeuse's outer atmosphere, tracing the exact path of Siwaha's orbit, much the way a boat leaves a visible wake behind it as it cuts through still water, a disturbance in its surroundings that persists and remains visible long after the boat itself has moved on. As Siwaha completes its close 6-year orbit, it appears to periodically disturb and help clear the material immediately around it, altering how much of Betelgeuse's light reaches Earth as the smaller star moves through different points along its path. It was, at long last, direct physical evidence connecting Siwaha's presence and motion to the exact 6-year brightness cycle that had puzzled astronomers for more than a century. Siwaha's orbit turns out to be almost uncomfortably close, carrying it no farther than roughly 4 astronomical units from Betelgeuse at its most distant, nearer than Jupiter's own orbit around our Sun, and, likely, close enough, at certain points, to graze the very outer edges of Betelgeuse's own bloated atmosphere. At those close passes, Siwaha may actually be moving directly through the outermost, thinnest layers of Betelgeuse's puffed-up outer atmosphere, plowing through diffuse stellar material, the way a snowplow might occasionally clip the edge of a snowbank, blown loose by the wind, rather than staying entirely on cleared pavement, stripping away and disturbing some small amount of material with each pass. That proximity carries a quietly sobering implication. Some researchers studying the system believe Siwaha's orbit may be slowly decaying, drawn incrementally closer to Betelgeuse with each pass. The likely culprit behind that decay is a process called tidal drag, the same basic gravitational tug-of-war that governs the slow, ongoing changes in the orbit of our own moon around Earth, though working here in something closer to reverse. Friction and gravitational interaction between the two bodies gradually bleed energy out of Siwaha's orbit, causing it to spiral inward by a small amount with each pass, so slowly that it would be undetectable within a single human lifetime, yet inevitable given enough time. If that trend continues, models suggest Siwaha could eventually spiral inward and be consumed entirely by Betelgeuse, possibly within the next 10,000 years, conceivably even before Betelgeuse itself reaches the end of its own story. For astronomers, the discovery carries significance well beyond satisfying a century of curiosity about one unusual star, confirming that a close companion can measurably influence a red supergiant's brightness, its surrounding material, and quite possibly its long-term evolution, gives researchers an entirely new factor to consider when studying other aging giant stars throughout the galaxy, many of which may harbor companions of their own that have simply never been detected. Some researchers have already begun re-examining archived brightness records of other well-studied red giants and supergiants with unexplained long secondary periods of their own, searching for the kinds of subtle signatures that might now be recognized for what they likely represent, having finally seen one confirmed example to compare against. Instruments only recently capable of detecting Siwarha are, by extension, only recently capable of detecting similar companions elsewhere, which means the number of confirmed cases is likely to grow substantially in the years immediately ahead. As astronomers apply the same techniques to other promising candidates, it also reframes a basic assumption many astronomers had long taken for granted, that a star as famous, as nearby, and as thoroughly studied as Betelgeuse had already given up essentially everything it had to teach. Instead, one of the best-known stars in the entire night sky turned out to be hiding a companion in plain sight for over 100 years. A reminder that even the most familiar objects in astronomy can still hold genuine surprises, provided the right combination of patient prediction, refined technology, and a bit of good fortune eventually comes together. Whether Siwarha's presence has meaningfully influenced Betelgeuse's own aging process, accelerating or altering it in ways a truly solitary star would not experience, is a question astronomers are only beginning to explore. A close companion can, in principle, strip away outer material, alter rotation, or otherwise disturb a star's structure in ways that ripple forward into how that star eventually ends its life. Untangling exactly how much of Betelgeuse's own unusual behavior over the past several years might trace back to Siwarha's quiet, 6-year orbit, rather than to Betelgeuse's own internal processes alone, remains an active and unresolved area of study. It is a question that matters more than it might first appear, because it touches directly on the single largest uncertainty still hanging over this entire story. Looked at one way, the entire arc from serious prediction to confirmed discovery took less than 3 years, remarkably fast by the standards of a mystery that had resisted explanation for over 100. Looked at another way, that swift resolution was only possible because of a full century of patient, unglamorous groundwork, generations of astronomers dutifully recording brightness measurements they could not yet explain, building the very archive that later made a confident prediction possible in the first place. Neither the slow accumulation nor the sudden breakthrough tells the whole story on its own. Both were necessary, and both, in their own way, defined how Betelgeuse finally gave up one of its oldest secrets. It is a rare thing for a single star to surrender 2 major, independent mysteries within the space of a few short years, after keeping astronomers waiting for generations. Between the explanation for the Great Dimming and the confirmation of Siwarha's existence and influence, 2 of the longest-standing mysteries surrounding this particular star, one nearly 6 years old in its rhythm, and the other over a century old in its puzzle, had both finally been resolved within the span of a few remarkable years. Every long-standing puzzle that had accumulated around Betelgeuse across more than a century of careful observation now had an answer, save for one. Only one significant question about Betelgeuse's future remained genuinely, seriously unresolved among the scientists who study it closely, and it happened to be the very question this story set out to answer in the first place. Not what has already happened to this star, and not what quietly orbits alongside it, but how much longer it actually has left before its final, inevitable ending arrives. Part 4. That single remaining question, how much longer Betelgeuse actually has, turns out to be far harder to answer than either of the mysteries already resolved. Explaining a dust cloud or confirming a companion star both involved detecting something happening on or near the star's visible surface, something telescopes could, with enough patience and the right instruments, eventually observe directly. Determining exactly how close a star is to its own core collapse means trying to understand conditions buried deep inside it, in a region no telescope will ever be able to see, hidden beneath thousands of miles of opaque, churning gas, where temperatures and pressures reach levels no laboratory on Earth could safely reproduce or directly sample. It is a little like trying to diagnose what is wrong with a pocket watch without ever being allowed to open its case, judging its condition only by how it ticks, how it feels in your hand, and how its hands move across its face. This is genuinely different from either of the mysteries already solved earlier in this story. The Great Dimming was, in the end, a matter of watching a cloud of dust drift through space, visible, physical, and directly measurable once astronomers knew where to look. Siwaha was a matter of finding a faint point of light in exactly the right place, at exactly the right time, difficult, but achievable with sufficiently advanced instruments, once the technology finally caught up to the challenge. The core of a star, by contrast, will never be directly visible from Earth. Not now. Not with any telescope currently being designed. Not for as long as Betelgeuse continues to exist as a star at all. Every conclusion about what is happening in there is, and will likely remain, an inference, drawn carefully from indirect evidence, rather than something anyone will ever simply see and confirm outright. What astronomers can observe directly is the rhythm of Betelgeuse's pulsations, the same swelling and contracting described earlier, along with subtle details about its brightness, its temperature, and its overall structure. From that outward rhythm, researchers attempt to work backward, using detailed computer models of how stars evolve, to infer which specific fuel the star's core is most likely burning at this exact moment. Every star of this size passes through a predictable sequence of fuels over the course of its life, hydrogen giving way to helium, helium eventually giving way to carbon, and so on through a series of progressively heavier elements, each stage shorter and more frantic than the one before it. That single detail, which specific link in that chain the core currently occupies, makes an enormous difference to the timeline. And on that single detail, two respected groups of scientists, working from much the same observational data, have reached genuinely different conclusions. One research group, led by astronomer Hideyuki Sayo, published an analysis in 2023, concluding that Betelgeuse's pulsation patterns most closely match a star already deep into a late stage of its life, one in which the core has exhausted its helium and moved on to fusing carbon, an advanced stage that immediately precedes the final countdown toward collapse. If that interpretation is correct, the remaining timeline would be startlingly short by astronomical standards, potentially only a few hundred years, or conceivably even less, before the core finally runs out of fuel entirely and collapses. A separate group, including researchers Meredith Joyce and Laszlo Molnar, reached a markedly different conclusion using much of the same underlying data. Their analysis suggests Betelgeuse's pulsations are better explained by a star still comfortably in an earlier stage, still fusing helium rather than carbon, a phase that can last for tens of thousands of years before the star moves on to the next, later stages of its life. Joyce and her colleagues have argued that certain assumptions about the star's physical size, built into the earlier analysis, may have skewed its conclusions, and that a more careful accounting places Betelgeuse's remaining lifespan on the order of tens of thousands of years at the very least, quite possibly closer to the commonly cited figure of about 100,000 years. Both interpretations rely on careful, legitimate science. Neither side is guessing carelessly, and neither has been shown to be simply wrong. The disagreement persists because inferring a star's precise internal fuel from its external behavior alone is enormously difficult, sensitive to small assumptions about the star's exact size, its exact mass, and the precise physics governing how energy moves through its interior. Assumptions reasonable scientists can weigh slightly differently and still arrive at defensible, well-reasoned conclusions that point in different directions. It is not unlike the way two experienced mechanics can listen to the same knocking engine and walk away with two different diagnoses, not because either one is careless or unqualified, but because the sound alone does not reveal everything happening inside. Only time and further evidence will eventually reveal which mechanic was closer to right, and even then, the confirmation is likely to arrive gradually through an accumulation of small refinements rather than in one single, decisive moment. As things currently stand, this disagreement remains genuinely unresolved, without a clear scientific consensus favoring one interpretation over the other. Both research groups continue refining their models, and future observations, along with improvements in how astronomers simulate the physics of dying stars, may eventually settle the question. Every year that passes without new evidence pointing clearly toward one interpretation or the other is not wasted time. Each additional season of careful brightness measurements, each new pulsation cycle fully recorded, adds another small data point that future researchers, perhaps using instruments not yet built, may eventually use to settle the disagreement between the two competing timelines. Whichever side eventually proves correct, the debate itself stands as a useful, humbling reminder that scientific consensus, when it exists, represents hard-won agreement rather than something owed automatically to any confident-sounding claim, and that its absence here is not a failure, but an honest reflection of a genuinely difficult problem. For now, however, the honest answer to how much longer Betelgeuse has left spans an extraordinary range, anywhere from a few centuries to roughly 100,000 years, depending entirely on which interpretation eventually proves correct. It is worth noting separately that astronomers studying supernova rates across the entire galaxy generally believe the Milky Way is due for a supernova of some kind, somewhere among its hundreds of billions of stars, within the coming decades. That statistic says nothing specific about Betelgeuse on its own. It reflects the broader rhythm of an entire galaxy full of aging stars, not a prediction about this particular one. Whenever the collapse does happen, whichever timeline eventually proves correct, the event itself will unfold with almost incomprehensible speed, a striking contrast to the tens of thousands, or possibly just hundreds, of years the star may spend approaching that moment. Once the core can no longer generate enough outward pressure to resist the crushing weight of everything above it, it collapses in on itself in a fraction of a second, an implosion followed almost immediately by a colossal rebound, a shockwave that tears back outward through the star's remaining layers and blows the vast majority of the star apart entirely. From the first instant of collapse to the star's outer surface finally being blasted apart, the entire process takes only a matter of hours, an almost unimaginably abrupt ending to a story that, depending on which research team eventually proves correct, may have been unfolding for tens of thousands of years. What remains behind, once the visible light finally fades years later, will likely be an extraordinarily dense, compact core, either a neutron star, barely larger than a modest American city, yet heavier than the Sun itself. Or, if enough material collapses inward, something even more extreme, surrounded by an enormous, slowly expanding cloud of debris carrying the heavier elements, the star spent its life creating outward into the galaxy. The same basic process, on a far grander scale, that first seeded the raw material for planets and eventually for life billions of years ago. Astronomers are not simply waiting passively for that light to arrive, either. Networks of specialized detectors positioned around the world, buried deep underground or beneath the ice of Antarctica to shield them from interference, continuously watch for a different kind of signal entirely, one that would actually arrive before the visible explosion does. In the earliest instant of a star's core collapsing, an enormous burst of nearly weightless particles, called neutrinos, escapes almost immediately, passing through the star's outer layers, and for that matter through the entire Earth itself, as though they were barely there at all, while the visible shockwave and resulting light take considerably longer to fight their way outward through all that overlying material. A sudden flood of these particles, detected simultaneously by observatories on different continents, would give astronomers a genuine early warning, likely hours before Betelgeuse's light itself became visible. Enough advance notice to turn every available telescope on Earth toward Orion's shoulder before the spectacle even began. This exact approach successfully provided advance warning ahead of the 1987 supernova mentioned later in this account. And the same global detector network stands ready today, watching quietly every single night for a similar burst that could come from Betelgeuse's direction at any time. There is one more layer to this uncertainty, stranger than either interpretation of the star's internal fuel, and it has nothing to do with disagreements between research teams. It comes down to simple geometry and the finite speed of light. Described earlier, the light reaching Earth from Betelgeuse tonight left that star's surface somewhere between 500 and 650 years ago, depending on precisely which distance estimate proves correct. That means the star you could step outside and find tonight is not necessarily the star as it exists right now, this very moment. It is the star as it existed centuries ago. Taken to its logical conclusion, this raises an honest, if slightly unsettling, possibility. If Betelgeuse's core collapsed at any point within roughly the last several centuries, sometime within the very window its current light has been traveling toward us, that collapse would already have happened. The star, in a very real sense, could already be gone. We simply would not know it yet, because the news, carried at the speed of light itself, has not yet had time to arrive. This is not a live scientific controversy, with researchers actively debating whether it has already happened. There is no evidence either way, and there cannot be, by the very nature of the situation. It is best understood not as an open question under investigation, but as an honest, permanent feature of how starlight works, the same way a letter already sealed and dropped in the mail carries news whose outcome is already decided, even during the days it spends traveling before anyone reads it. Whenever that moment does arrive, whether centuries from now or in the strange, unfalsifiable sense just described, possibly already decided, the practical experience of it, for anyone standing on Earth, has been calculated in careful detail, and it looks nothing like the doomsday scenarios that occasionally circulate online. When Betelgeuse's core finally does collapse, the resulting explosion will briefly become one of the brightest objects in Earth's night sky, rivaling the brightness of the half-moon. According to calculations based on the star's known distance and luminosity, it is worth being precise about what that comparison actually means, because it is easy to imagine something far less accurate. The light will not spread out and illuminate the sky the way moonlight does, diffused softly across the whole dome of night. It will be concentrated entirely into a single, brilliant point, the same size and position Betelgeuse already occupies in the sky tonight, only many, many times brighter, a beacon rather than a glow. For several weeks, that point of light would likely remain visible, even in broad daylight, a genuinely new star, seemingly appearing in the middle of the afternoon sky, bright enough, by some estimates, to read comfortably outdoors, after dark, by its light alone, the way earlier generations might have read by a particularly bright full moon. That extraordinary daylight visibility would likely last somewhere in the range of 2 to 3 months before beginning a slow, gradual fade. Even after the daylight brightness passed, the new light would remain easily visible to the naked eye after dark for a year or more, slowly dimming night after night, month after month, as the visible debris from the explosion continued expanding and cooling. Long after it faded below naked eye visibility, it would remain a target for telescopes, professional and amateur alike, for years or decades to come, a slowly fading ember of light marking exactly where, in Orion's shoulder, a familiar star used to be. Because Orion sits so close to the celestial equator, as established earlier, that eventual burst of light would be visible from nearly every inhabited place on the planet, not merely from one hemisphere or region. Someone walking home after a late shift in Tokyo, someone tending a fire on a camping trip in the Rocky Mountains, someone finishing a late dinner on a patio in Buenos Aires, all looking up at very different hours of their own day, would eventually be able to find the same extraordinary new point of light in roughly the same patch of sky, a rare astronomical event genuinely shared across nearly the entire human population within the same handful of days. Nothing on quite this scale has happened within our own galaxy in living memory. The last supernova confirmed to have occurred within the Milky Way was observed in 1604, 422 years ago, by astronomers including the German scientist Johannes Kepler, whose detailed observations at the time earned the event its common name, Kepler's supernova. Kepler was not the only person to notice it, but his methodical observations, recorded over the following months as the new star gradually faded, became the most complete scientific record available, and it happened during a period when the prevailing understanding of the cosmos still held that the heavens beyond the moon were fixed, unchanging, and permanent. A sudden new star appearing, blazing, and then slowly fading away over the following months directly challenged that old assumption, contributing to a broader shift in how people understood the nature of the night sky itself, a shift that helped pave the way toward the modern understanding of stars as objects with their own births, lives, and eventual deaths, rather than fixed, eternal lights nailed to an unchanging dome overhead. Historical records indicate the 1604 supernova remained visible during daylight hours for roughly 3 weeks. Betelgeuse's own eventual supernova, given its far closer distance, would likely surpass that display considerably in both brightness and duration. Since 1604, the only supernova visible to the unaided human eye occurred in a neighboring galaxy, not our own, observed in 1987, 39 years ago, and catalogued accordingly. That means no one alive today, and no one who has lived within the last 4 centuries, has ever witnessed a supernova occurring within our own galaxy. Whenever Betelgeuse's moment finally arrives, it would be the first such event visible to the unaided eye from within the Milky Way in over 400 years. Despite the extraordinary brightness involved, none of this poses any danger whatsoever to life on Earth. Supernovae can, in principle, pose a genuine hazard to nearby planets through bursts of radiation capable of damaging a planet's atmosphere, but only for stars sitting far closer than Betelgeuse does, generally estimated at somewhere under 200 light-years, with some of the most conservative estimates placing the danger threshold closer to 50 light-years. Betelgeuse, at somewhere between 500 and 650 light-years away, sits comfortably beyond even the most cautious version of that danger zone, several times over. There is also no meaningful risk from the kind of narrow, highly focused burst of radiation that some of the most massive, fastest-spinning dying stars occasionally produce along their poles. Betelgeuse shows none of the telltale signs associated with that particular, much rarer category of explosion, and even if it did, Earth would need to sit almost perfectly in the path of that narrow beam for it to matter. A geometric coincidence, with no evidence supporting it in this case. Life on Earth would experience Betelgeuse's eventual supernova purely as a spectacle, an extraordinary, once-in-many-lifetimes sight to witness, with no measurable physical consequence beyond the light itself. Siwaha's own fate in that moment is easier to guess at than to formally predict, even without a dedicated study to confirm it. A star orbiting this close, well within reach of anything resembling a supernova's outward blast, would almost certainly be swept up in the destruction, its delicate, 6-year orbit obliterated in the same violent instant that ends Betelgeuse's own long life. The bracelet, in other words, would not survive to circle an empty space where a hand used to be. Whatever the exact mechanism, the two objects that have shared a close, quiet orbit for who knows how long would very likely meet their most dramatic moment together. Whether Siwaha has already spiraled inward and been consumed by then, or whether it is still orbiting nearby when the end finally arrives. In the meantime, the monitoring continues, much as it always has, only now with far more instruments, far more attention, and far more understanding than at any point in the star's long observational history. Telescopes across the world and in orbit above it continue tracking Betelgeuse's brightness, its pulsations, and the ongoing influence of Siwaha's close, 6-year orbit, alert for any sign that might indicate the calculations are shifting, that the countdown, whatever it truly is, has entered its final stages. So far, nothing in the data suggests an ending is imminent in any human sense of the word. No evidence that tonight, or next month, or even next year, is meaningfully more likely than any other point across the vast range still under discussion. Knowing all of this changes the experience of looking up, even if the star itself looks exactly the same as it always has. What used to be simply a bright, reddish point marking a hunter's shoulder now carries the weight of an entire, still unfolding story. An ancient name born from a translator's small mistake, a companion star hiding in plain sight for over a century, a violent eruption caught almost by accident, and an ending already decided, but not yet dated. None of that changes what you would actually see if you stepped outside tonight and found it for yourself. It would look exactly as it always has, steady, familiar, and quietly orange-red against the winter dark, giving no outward sign of everything now known to be happening and still unknown underneath. There is something worth sitting with in all of this, now that every piece of the story has finally been laid out. A star whose light left it long before Johannes Kepler ever spotted his own supernova in the sky above Europe, whose most basic mysteries have only been solved within the last few years, and whose ultimate fate remains genuinely, honestly, uncertain, even to the scientists who study it more closely than anyone alive, has been hanging quietly in the winter sky this entire time, waiting to be understood, indifferent to whether anyone below ever managed to understand it. 400 years ago, nobody watching that same point of light had any idea it was a red supergiant at all, let alone one nearing the end of its life. 100 years ago, nobody knew about the strange 6-year rhythm hiding beneath its more obvious pulsation. Even a handful of years ago, nobody knew about Siwaha, quietly circling closer than Jupiter circles our own sun. Each generation of watchers has known this star a little better than the one before it, without ever quite catching up to it completely. Every astronomer who has ever spent a career patiently returning to this one star, every amateur stargazer who ever logged a single brightness measurement into a shared record without knowing whether it would matter, every naming committee that ever debated which word best honored a newly confirmed companion has been quietly participating in the same long, unfinished project, trying to understand something that will finish on its own terms, regardless of how well anyone manages to understand it beforehand. That is not a discouraging thought. If anything, it is closer to the opposite. There is a particular kind of privilege in being allowed to watch, closely and carefully, something whose outcome you cannot control and whose timing you cannot know, simply because you happen to be alive during the small, fortunate window when the tools finally existed to watch it properly. Every person who has ever looked up and found that reddish point of light in Orion's shoulder, going back through every generation of every culture that ever named a hunter out of those same stars, has been looking, without realizing it, at a star already living in the final chapter of its story. Not a star approaching that ending, but a star already inside it, a status that has held true for longer than anyone currently alive has been alive. The ending itself is no longer in question. Physics does not offer second chances or alternate outcomes. Once a star has reached the size and age Betelgeuse has reached, what remains genuinely open, what even the finest instruments and the most careful scientists in the world still cannot say with confidence, is only the calendar, a single missing number in a story where every other detail has, at long last, been filled in. None of this requires resolution to be worth understanding. The urge to want a firm answer, a specific year, a countdown clock ticking down toward a known date, is a very human impulse, understandable and entirely natural. But the universe was not built to satisfy that particular impulse, not for this question, and perhaps not for most of its biggest questions. Some things simply take as long as they take, unfolding on a schedule that has nothing to do with human patience, human curiosity, or even humanity's genuinely remarkable ability to build instruments capable of detecting a companion star from hundreds of light years away. Betelgeuse will end when Betelgeuse ends, on its own terms, at its own pace, indifferent to every deadline, every headline, and every hopeful guess anyone has ever offered about when that ending might arrive. That sentence is not a shrug. It is closer to a kind of respect. There is a particular kind of peace available in accepting that distinction between what is certain and what is simply unknown, rather than treating the two as the same problem. Betelgeuse's ending is not a mystery. It is a certainty, written into the physics of stars this size the moment they are born, as fixed and unavoidable as anything in the universe gets to be. Only its timing resists an answer, and only its timing was ever going to. That is not a failure of science, and it is not something to be anxious about while waiting for a more precise number to eventually arrive. It is simply the shape of this particular kind of knowledge, the same way you can be completely certain, lying in bed tonight, that sleep is coming for you eventually, without being able to say exactly which minute it will arrive. You do not usually spend those final waking minutes anxiously calculating the exact moment. You simply let it come, trusting that it will, in its own time, the way it always has, for every person who has ever closed their eyes not knowing precisely when rest would finally arrive, only that it would. Anyone who wanted to become part of that same long tradition of careful watching, the one that stretches back through generations of amateur observers, and now includes networks of professional instruments spanning the globe, could, in principle, start tonight, with nothing more than a clear sky, a bit of patience, and the simple recurring act of looking up and finding that same reddish point of light in exactly the spot it has always occupied, exactly the spot it will likely still occupy tomorrow night, and the night after that. Somewhere above you tonight, whether the sky happens to be clear where you are or not, Betelgeuse continues doing exactly what it has been doing for longer than written history, burning through what remains of itself, one reaction at a time, moving steadily and irreversibly toward an ending that has already been decided, on a schedule that belongs entirely to the star itself and to no one else. It was already like this the first time anyone ever pointed at that reddish light and gave it a name. It will likely still be like this the next time you happen to look for it. Nothing about that changes what it truly remains: a familiar, ordinary-looking point of light, quietly finishing a story that started long before any of us arrived to watch, and that will end exactly when it was always going to end, regardless of whether we ever manage to find out precisely when. Drift off gently. Orion's shoulder still burns, keeping its own quiet time.